let's finish our talk about gases. Here's the combined gas law. Now, I showed you guys a way to solve these kind of problems where you have initial and final conditions, and you plug it into what I call the logical ratio methods, where you look and one goes up, the other goes down, P equals nRT. If it's on the same side, it's inversely related. If it's on opposite sides, they're directly related. You can also use that algorithm, that formula, depending on which variables you're using, pressure, volume, or temperature, and you don't have to use all of them. You should also be able to decide not only whose law is whose, but what algorithm relates to that person's law. All right, so that's an important part too. And that's what we call the combined gas law, which is Piv-Nert and the relationships between the variables. All right, let's try a combined gas law problem. It says here, a nitrogen gas sample occupies 50 mils at negative 80 and 1250 torr. What's the volume at STP? Now, we sort of did this last week a little bit. So we've got, I'm going to put initial and final conditions. I'm going to make the grid here. You guys should be making the grid there. And the variables we've got to deal with are volume, we've got temperature, and we've got pressure. My initial volume is 50.5 milliliters. My initial temperature is negative 80 degrees Celsius. And my initial pressure is 1250 torr. And they want to know what's the volume at STP. And what is STP? What are the values? 25 degrees Celsius and 1 ATM. All right, so let's look at this problem. And this is one that we sort of went over last week, but I want to review. This is a good problem to do that. All right, so there's our information I've summarized from the actual problem. But we've got to do something with the numerical values in this. What do I do to the numerical values in this?
Change Celsius to Kelvin.
I got to change Celsius to Kelvin for sure. All right, so 273 and negative 80. Right, so it starts at negative 80, and I got to add 273 to the value to get the Kelvin temperature. Did I do that right? 193? That's right, Kelvin. All right, 25 Celsius plus 273 is 298 Kelvin, right? All right, so we changed our temperatures. What else should I do?
Change ATM.
One of the two. I prefer in these kind of problems to always use the Piv-Nert best value. Since R is liters times ATM per mole times Kelvin, it's best to have all the other variables in those particular units, just so that R, if you ever have to use it, can be used. So in this case, I'm going to change the torrs to ATM. So 1250 torrs, and I want to go from torrs to ATMs. And what's the numerical values that gets me from torrs to ATMs there? Torr, I think, is 760 to 1 ATM. I gave that to you the first day of the gases. I think that's the conversion factor. So somebody with a calculator, what's 1250 divided by 760? What number do we get? 1.6? We'll just put 1.64. So 1.64 ATMs. All right, now I can go in and plug it in, and I'm going to do this both ways. I'm going to do it with my method. I'm going to also use the algorithm method. So let's try my method first. Here's our x. This is our variable, so that's the number I need to start with. Absolutely, we need to change that to liters. So how do I do that from milliliters to liters? Move the decimal how many places?
3.
1, 2, 3. So I got 0.0505 liters to start with, and I'm going to need two ratios or proportions that's going to affect the volume in the way that those ratios or proportions are being affected themselves. So let's look at temperature first. What's happening to temperature? Is it going up or down? Up. Temperature's going up, and we know that Piv-Nert if they're on the same side of the equation, in this case, volume and temperature on opposite sides, so what does that mean about their relationship? Directly. All right, so that if temperature is going up, what's that going to do to volume? It's got to go up by the same proportion. So I want that number to get bigger based on a ratio I'm going to create out of the temperature values. So I want that number to get bigger, so which one of those am I going to put on top?
298.
The 298 on top, because I want that one to get bigger, and the 193 on the bottom. All right, so now what I do in my bookkeeping method that I like to use is I cross out the arrows so that I know that I've taken care of that particular relationship already. Now when I go on to the relationship between pressure and volume, I consider those independent of the last relationship that I just dealt with. All right, so now that was my temperature relationship. Now I've got to take care of my pressure relationship. What's happening to pressure here? Pressure's going down. And since pressure and volume are on the same side, their relationship is inversely related. So if pressure's going down, what's that got to do to volume? Volume's got to do what? It's got to go up by the same proportion. So I want that number to get bigger out of a ratio I create with those numerical values. So if I want that number to get bigger, which one of those would I put on top? 1.64 and 1.0. All right, now it's just a matter of pushing it into the calculator. You punch that number in first, and here's where parentheses buttons come in, super handy. That number first times, open parentheses, 298 divided by 193, close parentheses, then push enter. Make sure you push enter in between. Then times, open parentheses, 1.64 divided by 1.0, close parentheses, then enter, and what do we get? And what would my units be here? Liters. And that seems reasonable, right? Because we decided that volume was being affected by increasing it for both variables in this case. And so this number should have got proportionally larger. Let's look at the algorithm method. If we take this and we solve it and we get all the variables on one side for r, PV over nt is equal to PV over nt. And you can say prime, 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 2, 2, 2, 2, or initial conditions, right? And these are final conditions. You can consider them. All right, now we're not using all these variables because the amount of gas didn't change, right? So we don't need N. The same amount of gas was in the container here in this problem. But we did have pressure, volume, and temperature values to deal with. So I can take this algorithm, right, and I can just plug and chug the numbers in. Engineers, you're going to like this. Plug and chug. The first pressure, I've already changed it, and I would advise no matter what method you use is to keep track of your variables using a tic-tac-toe kind of method here because it helps, it really does. All right, so we plug and chug. The initial pressure in this case is 1.64 ATMs. The initial volume, changed it to liters, remember, 0.0505 liters. My initial temperature here is 193 Kelvin. Now I can set that equal to my final pressure, in this case 1 ATM, my final volume, which I don't know, I'll say is X, divided by my final temperature, in this case 298 Kelvin. All right, so a lot of people might like this method better, and that's fine, as long as you get the right answer. You might want to use both. Right? In algebra class, didn't they always have you check and plug the numbers back in for the variable and see if the original expression was solved? That's always a good idea. The problem arises if the variable is on the denominator and you just start moving things around. We all know with some algebra we can take 298 and do what with it to get it? Do it over on this side, right? And then what could I do with the 1 ATM to get it over on the other side? Put it on the bottom, on the numerator, right? So now I have x over 1. Which is what we want algebraically. So now if you plug all those numbers in, you should get the same exact answer, which is 0.128 liters. All right? So two ways to solve that kind of problem, if you like the plug and chug or if you like the logical ratio conversions kind of method.
I have a question.
Yes?
So in the book, where you have 298, they're putting 273.
Are they calling standard temperature 0 or are they calling standard temperature 25? Because that's where I've seen a smidge of disagreement amongst authors and scientists is standard temperature 0 or standard temperature 25? What do they tell you in your book? Do they say it's 0?
0. Yeah.
Okay, so that's probably where it's coming from. You know what? Let's look it up on the internet. Let's see what the common...
One in Google.
That's right. Google solves everything, right?
What is the meaning of
This doesn't mess up my screen here. All right. What is STP? That's a good question. I've seen it in both. There we go. Socratic. Oh, we don't know if we want the Socratic method. 273. All right. So this particular website says 0 degrees Celsius. Let's check and see if there's any other agreement here. Standard temperature and pressure. Here it's 273.15. So I guess we have to change our paradigm. That's where it comes from. We have to change our paradigm and decide. So this would change our numbers here, right?
Yeah.
So that's not 25, that's 0, which is now 273. Then that changes what number? Where's the 298? Here we go, 273. And this one is now 273. So what's my new answer?
7.
What is it?
Makes it 1 or 0.177. 117.
117
Yes.
liters. Okay. All right. Small change in our paradigm. All right. Let's see here. I know there's another good problem on the PowerPoint. Let's see if I can find it here. There it is. All right. All right, here's a good one. How many moles of hydrogen gas occupy? This is a different kind of problem. This is an ideal gas law problem. So let's see, how many moles of hydrogen, so the question is how many moles of hydrogen gas occupy 0.5 liters, 0.500 liters at STP. All right, new kind of problem. If you like math, this is the unit for you, all right? We've got a ton of math going on here. All right, here's our problem. Now this is a different kind of problem. The first kind of problem that we looked at, they give you initial and final conditions of 2 or 3 things, and you have to find the final condition of one of them that's missing. In these kind of problems, they're going to give you some information, and of the PIV-NERT pieces of information, you will have 3 of the 4. There's 3 big genres of gas law problems. The first one was the one we just went over with pre and post conditions. Now you'll have one where you have 3 of the 4 pieces. All right, so let's decide what pieces we have based on the information they've given us in the problem here that we could use to plug in to PIV-NERT. Okay, what's this piece of information? There's the volume. All right, so right off the bat, I know I can plug in 0.500 liters as the volume. But they're also telling us something else that we just changed our paradigm on. STP means what? 0 degrees Celsius and 1 ATM. So we have some other piece of information. What other piece of information do we have?
pressure and temperature?
We've got temperature and we've got pressure. So we changed that. There is authors who say 25 is standard, and apparently Corwin likes 0, so we're just going to go with 0 because that's probably what the test bank is based on. All right, so if we take 0, we got to do what with 0? 273 Kelvin, and atmospheres is already in the right units, so now we just plug in for P. I'm going to plug in my 1 ATM equals N. What's N? Number of moles. Do we know that? No, but that's what we've got to find out, right? Isn't that what we're finding out? So N, and what's R? I think I told you guys what R is already, but
That's at 0.0821.
liters times ATM per mole Kelvin, right? And then what's my temperature? 273. All right, now I think we could all use some algebra here, right? Algebra's our friend. What would I do with some algebra to solve this expression?
Just cross out the,
Well, I got to cross them out, but to cross them out, I got to move them somewhere. Where would I move this one?
to the other side,
Where on the other side?
on the bottom.
On the bottom is the numerator. And
Can you
then,
move the other one to the bottom too?
sure. All right, and then that gives us n over 1, which is good. We don't want 1 over n, we want n over 1. And now somebody with a calculator, what's 0.5 divided by, open parentheses, 0.0821 times 273, close parentheses. So you don't open and close the parentheses here in your calculator. You open it, you put that times that, and then you close the parentheses. And what does that give you?
0.0223.
And that is, what are my units here? Moles, right? Let's double check. Kelvin cancels, right? Liters cancels. ATMs cancels. And moles is on the bottom, but since that's a unit that's in the denominator, when it resolves, it comes up to the numerator. So we have moles of what? Of H2. All right, what if they said how many grams do you have? Could you do that? You could do that, right? We could go from moles of H2 to grams, bless you, of H2. I think that's a 2.0, right? So that'd be pretty easy to do. Okay. So PIVNERT, you just got to solve using the information that you have, the 3 of the 4 pieces. All right, I'm going to make up a problem, one PIVNERT problem that I kind of like. We have a big Goodyear blimp. Do they still have that thing that flies around anymore?
Yeah.
There was a great terrorist story when I was in high school, and it was about a terrorist organization that got a hold of the Goodyear blimp, and they put a bomb in it that was going to spray a whole bunch of like shrapnel and stuff, and they drove it over a giant stadium during a huge football game. I don't want to tell you the ending. I forget the name of the movie, but it was really good. It was way before 9/11 or any of that stuff. All right, so we got a Goodyear blimp, and it is enormous. We're going to say that it holds 2 million, is that million? Liters. Okay, it's enormous. Is that 2 million or is that, no, that's 200 million. Okay, we're going to have a huge, enormous 200 million sized Goodyear blimp. Those things are huge. I wouldn't be surprised if it was 200 million liters, right? And it's up in the air where it's pretty cool, and we'll say the temperature up there where it's pretty cool is about 12 degrees Celsius. And the pressure up there high in the atmosphere as we're flying over the stadium is going to be less than ground level pressure, so we'll say it's 0.820 ATMs. And I want to know if I'm going to pump this thing full of, now do they put hydrogen in these things or helium? Remember well, they used to put hydrogen, right? They used to put hydrogen. Remember the Hindenburg? Yeah, they changed their mind on that one. Yeah, that was not super successful. I'm not sure what they put them in anymore. Let's just pretend they put, what do we want to pick, hydrogen or helium?
Helium.
Helium, all right.
Doesn't blow up.
All right, so we'll pick helium, right? We'll pick helium. So ours is a safe one. Ours is a safe one. And I want to know how many grams of helium am I going to need to fill this sucker up? Just a couple? A couple grams?
6.02.
All right, so we know that this is true, right?
Moles per
So what numbers would I plug in?
all pressure.
Almost all.
Pressure.
Pressure is right there, right? 0.820.
ATM.
What's my volume?
200 million.
200 million liters. That's a honking huge balloon. What's N?
That's the one we gotta find.
We don't know. That's what we need to know, right? Then we can convert.
And then 0.821 liters times.
And the last one is, what do we got to do with this number?
Convert it to Kelvin.
To Kelvin, so 273, 283, 290, 283, 285. And it's the same kind of problem as the last one, right? Then you just got to convert to grams of helium.
So then you move everything over to one side.
Yep, move these over here. And then once you know how many moles of helium, you go from moles of helium to grams, which is, how How much does helium weigh? 4? 4. There it is.
But wouldn't helium gas be Hg2? Or no?
Nope, helium is monatomic. Helium is monatomic. It's one of those. The noble gases are all monatomic. Helium, neon, argon, krypton, xenon, and radon are all monatomic. All right, so that's the second of the types of genres of gas law problems. The third and last type of gas law problems involves our favorite friend, stoichiometry.
Oh, beautiful.
Aren't you happy you guys love stoichiometry so much? Everybody did so good on the last exam. All right, so we're adding one more leg of the journey onto our stoichiometry flow chart, or our stoichiometry wheel, I think they call it in the tutoring center. That's all right. Remember, we always started with moles of A. We go to moles of A to moles of B, right? And that's the balanced equation that gets us to that point. And that's why my advice for solving chemistry problems is always twofold. If you have no idea where to start a chemistry problem, what's the two things you always do? Find moles out of something, and then look at the balanced equation, consult the balanced equation. All right, so we already know we can go from grams using the molar mass. We can go from number of particles using Avogadro's number. We can go from liters of aqueous solution using molarity, right? And we can now go, let's see, we also did liters of gas using 22.4. Does anybody know what this number is, 22.4? All right, 1 mole of any gas occupies, any gas, I'm going to put a little caret here, at STP. Remember, STP now we decided is 0 degrees Celsius and 1 atm, occupies a volume of 22.4 liters. Now it's got to be at STP. And this is one of Dalton's premises in gas law problems, that because the particles of the gas are so small and insignificant compared to the volume that they take up, that they all occupy the same exact volume if they are at those conditions, which is standard temperature and pressure. So if you have liters of gas, you can use this 22.4 number just like you can use molar mass, Avogadro's number, or molarity to get you from liters of gas to moles. And then once again, you can go from those things back in the other direction. And this is your full stoichiometry flowchart now. Liters aqueous, and then liters of gas, right? So same type of thing. All right, let's try some gas law problems. And I'm going to start with my favorite gas equation, the Haber process, which takes nitrogen and hydrogen gas and makes ammonia out of it. Now to balance this, I know we need a 2 there and a 3 there. And the reason I like this gas equation is each of the coefficients is different, so it helps us make a comparison. All right, say for example, I'm starting out with, I got 1.2 grams of nitrogen gas, and I have 50 grams of hydrogen gas. I want to know how much in liters NH3 can I make? And it's at STP. So I'm carrying out my reaction at standard temperature and pressure. All right. Well, remember stoichiometry? What's the first step in stoichiometry? And this is a limiting reagent problem. How do I know this is a limiting reagent problem? Right, so I've got something of this and something of that, and I got to figure out which one's going to run out first. So what's the first step in a limiting reagent kind of problem? Convert everything to moles. All right, so we got 1.2 grams of nitrogen, and we got to go from grams of nitrogen to moles. See, nitrogen weighs 14 grams per mole, and there's 2 of them, remember? So that's 28 grams per mole. And then I got 50 grams of hydrogen. And hydrogen is only 2 grams per mole. So what's 1.2 divided by 28?
0.043.
So that's your limiting reagent.
So, did I do that right? Did I put the numbers in right?
Don't you have to multiply or divide by moles too? Because it's
Right, now you have to divide by what number?
by 3.
By which one?
Well, the bond.
3, and that one's by 1. So 25 divided by 3 is what number?
Is 8.33. Oh, repeat.
8.3. Okay, so that's just a number, so that doesn't have any units. And this one is going to be 0.043. So which one is the smaller number? All right, so that's going to be my limiting reagent. And I always put a little note to myself so that I know where to start. And that was kind of deceptive. You go, oh, 1.2 grams of that, and I got 50 grams of that. You'd think that right off the bat that would be the limiting reagent. Well, it wasn't deceptive. It was true. 0.043 moles of N2. Now, what am I going to do there? If I consult my stoichiometry flow chart, I already have moles, right? I have moles. So now I'm here. Now I got to go from moles of that stuff to moles of what? Moles of the other thing that I'm interested in. What other thing am I interested in? The NH3. So I'm going to go from moles of N2 to moles of NH3. Right? That's the step I just went through right there, because I already figured out my moles in my previous calculation. So now I want to cross that mole bridge ratio and go over here. Is it 2 to 1? All right, so we got, 2 to 1. All right, now moles of N2 cancels. Now where do I want to go? Sorry about that. Moles of N2 cancels. So I'm going to go moles of NH3 to what? To liters. Liters of NH3, right? If I look at my stoichiometry flow chart, I was here, and I wanted to go to liters because in the problem they said, how much in liters of the NH3 am I able to make? So after I went to moles of the second thing, I have to go to liters. And to go to liters, I'm going to use this 22.4 because in the problem they told me it was at STP. So that's the key. So then with the calculations, what I'm going to do, 1, right, moles to anything else. Moles to anything else. The 1 always goes in front of moles. Now what's the number in front of it? 22.4. All right, with the calculator then, 0.043 times 2, enter, times 22.4, and what do we get?
1.93 liters.
There you go. Easy peasy, huh? Since you guys all know stoichiometry so well. All right, let's see, do I have any more gas law calculations on the PowerPoint that we could go over? Let's check and see. Did that one. And there's the summary. Oh, something interesting. If you forget what R is, let me show you how you get R. Here's a question somebody asked me once. And R has a lot of values depending on which scientist is using it. Physicists have one value for R, chemists have a different value for R, and it's based on this idea of Pivnert at STP. All right, so if we want to solve for R, algebraically, if I want to solve for R, what would I do? PV over NT. All right, if I plugged in all the conditions that are standard, right? What's standard pressure? 1 atm. Standard volume of 1 mole of gas is 22.4 liters. 1 mole is standard, right? That would make sense. What's the standard value? 1 mole. And what's standard temperature? 273 Kelvin. All right. So now if you plug all those in, you come up with 0.0821. And what are my units? liters times ATM per mole times Kelvin. That's where R comes from, is the standard values for everything. All right, that's it. That's it for gas laws. I can't think of anything